James Clerk Maxwell was born on June 13, 1831, at 14 India Street in Edinburgh, Scotland. He came into the world during a period of profound scientific awakening in Europe, yet his early surroundings were far removed from the bustling intellectual centers of the continent. His family, part of the minor Scottish gentry, offered him a quiet and stable childhood. His father, John Clerk Maxwell, was a lawyer and landowner, and his mother, Frances Kay, came from a cultured and intellectually inclined family. These parental influences would quietly shape James's early sensibilities, both intellectually and morally. Shortly after his birth, the family moved to their country estate, Glenlair, located in the rural hills of Kirkcudbrightshire. This serene environment provided young James with both freedom and inspiration. The natural landscape, with its rivers, rocks, and wildlife, became his first laboratory. From an early age, Maxwell demonstrated an unusual curiosity about how things worked. He would often ask questions well beyond his years, earning him the family nickname Dafty, a term of endearment, reflecting both affection and bafflement at his intense curiosity. Maxwell's mother, who was exceptionally well educated for her time, took on the role of his first teacher. She introduced him to reading, arithmetic, and basic science, instilling in him a disciplined habit of observation and inquiry. Unfortunately, Frances Maxwell died of abdominal cancer when James was only 8 years old, a loss that would leave a significant emotional imprint on him. Her early guidance, however, had already sparked a lifelong passion for learning that would never diminish. After his mother's death, James's education was overseen by tutors, although many of them struggled to match his intellectual energy. Recognizing the limitations of home education, his father enrolled him at the Edinburgh Academy in 1841. It was here that Maxwell's intellectual gifts began to draw formal attention. At first, his eccentric behavior and rural accent set him apart from his classmates, but his academic brilliance soon earned him widespread respect. He quickly surpassed his peers in mathematics and natural philosophy. At the Academy, Maxwell came under the influence of several notable instructors, including James Forbes and Philip Kelland, who encouraged his mathematical interests. It was during this period that he began to develop a methodical approach to geometry, experimenting with oval curves and writing his first scientific paper on the description of oval curves. This was an extraordinary achievement for a 14-year-old and revealed not only precocity, but also a deep conceptual understanding of geometry and algebra. Maxwell's early work with geometrical figures was more than just an academic exercise. It indicated an innate capacity for visualizing complex abstract systems, a skill that would later prove critical in his theoretical physics. Even in his youth, he was not content with simply solving problems. He wanted to understand the underlying principles that govern natural phenomena, a trait that would become central to his scientific identity. Despite his brilliance, Maxwell remained grounded and humble. His letters from this period show a combination of intellectual seriousness and childlike wonder. He was not a solitary prodigy. He enjoyed practical jokes, outdoor games, and long walks in the countryside. This balance between rigorous thought and a zest for life made him both an engaging student and a well-rounded individual. Maxwell's intellectual maturity was matched by a growing sense of ethical responsibility. From his early years, he exhibited a quiet but profound moral compass, likely a product of his Presbyterian upbringing and the Stoic values of his Scottish heritage. This ethical dimension of his personality would later surface in his integrity as a researcher and educator, as well as in his deep concern for the responsible application of science. By the time he reached his mid-teens, Maxwell had already developed a framework of thinking that was both analytical and creative. His early exposure to natural surroundings, combined with disciplined instruction and personal hardship, had forged a mind attuned to the nuances of both the physical world and human experience. These formative years laid the bedrock for a career that would revolutionize our understanding of the universe. The corridors of the University of Edinburgh were charged with an atmosphere of intellectual rigor and debate when James Clerk Maxwell first stepped through its gates in 1847. He was just 16 years old, still bearing the quiet demeanor and thoughtful curiosity that had defined his childhood, yet already poised to ascend into realms of academic sophistication. Though many students at the time viewed university as a stepping stone to professions in law, medicine, or the church, Maxwell saw it as a vessel of exploration, a place where nature's deepest patterns awaited discovery. In the lecture halls, he encountered a vibrant academic community. The university, though not as elite as Cambridge or Oxford in prestige, boasted a robust tradition in natural philosophy and mathematics. Here, Maxwell came under the instruction of eminent scholars like James Forbes, a physicist who had studied glaciers and heat conduction, and William Hamilton, a philosopher and logician whose lectures on metaphysics fascinated the young student. Though he didn't always agree with his professors, Maxwell absorbed their teachings eagerly, weaving them into the fabric of his own developing worldview. He did not confine his studies to the classroom. Long evenings in his small study room were spent poring over treatises on mathematics and mechanics, his mind energized by unanswered questions. His notebooks from this time are filled with complex diagrams, symbols, and exploratory equations, early signs of the deeply visual and analytical mind that would characterize his later work. The tools of Euclidean geometry and Newtonian mechanics became the lexicon through which he began interpreting the world around him. It was during his Edinburgh years that Maxwell's fascination with the properties of light and color began to crystallize. Using simple instruments of his own design, spinning discs, prisms, colored paper, he began to investigate how colors could be synthesized and perceived. Though he lacked access to advanced optical equipment, his results were remarkably insightful. His ideas hinted at an internal model of vision and color mixing, something few scientists had previously attempted to formalize with mathematical precision. Yet, even as his ideas matured, Maxwell felt the constraints of his environment. Edinburgh, while intellectually rich, could not offer the depth of mathematical instruction or peer collaboration he craved. By 1850, with his father's support, he transferred to the University of Cambridge, enrolling at Peterhouse before switching to Trinity College, which offered a more mathematically intensive environment. This move marked a decisive shift in his intellectual development. At Cambridge, Maxwell found himself in a crucible of mathematical excellence. Surrounded by some of the finest minds of his generation, he was both challenged and inspired. The Tripos examinations loomed large, a grueling series of tests that determined a student's academic rank and future prospects. Maxwell prepared for them with characteristic diligence, yet he remained independent in thought, often approaching problems with unorthodox strategies. In 1854, he graduated as second wrangler, a title that indicated he had placed second in the mathematics tripos, and shortly afterward, he won the prestigious Smith's Prize for mathematical research. What set Maxwell apart was not only his academic success, but his inclination to see mathematics as a language for describing reality. He believed equations could do more than solve problems. They could express the essence of physical laws. While his peers often focused on specific problems, Maxwell was already seeking unifying principles, looking for the invisible threads that connected disparate phenomena under a common theoretical umbrella. Cambridge also gave Maxwell the opportunity to publish and share his findings with a broader audience. His early papers, published in the Cambridge and Dublin Mathematical Journal, addressed topics like geometrical optics and the theory of rolling curves. But what drew the most attention was his work on the general theory of equilibrium figures, how masses deform under rotation. His writing was dense yet elegant, structured with clarity and built upon rigorous logic. Though still young, he was beginning to establish a reputation among Britain's scientific elite. Socially, Maxwell remained somewhat apart from the cliques and rivalries that characterized academic life. He was friendly, often humorous, and deeply principled. He preferred long conversations about philosophy and science to idle gossip, and kept correspondence with both students and professors. Those who met him were often struck by the contrast between his youthful appearance and the depth of his intellect. In debates, he was precise and composed, rarely raising his voice, yet his arguments carried weight and often concluded discussions. By the end of his time at Cambridge, Maxwell had evolved from a curious boy of Glenlair into a formidable thinker. The intellectual foundation laid during these formative years would support the weight of theories that would reshape physics. The stone walls of Trinity College, with their centuries-old traditions and rigorous academic climate, became the backdrop against which James Clerk Maxwell began to sharpen the tools of theoretical science. As he settled into the intellectual rhythms of Cambridge in the early 1850s, Maxwell was no longer a budding talent. He was quickly emerging as one of the most promising minds of his generation. Though still modest in demeanor, there was an undeniable intensity to his method of thinking, an eagerness not just to solve puzzles, but to illuminate the deep principles hidden within them. Unlike many of his contemporaries, Maxwell was not content to merely demonstrate mathematical prowess through rote computation. Instead, he pursued elegance and unity in his reasoning. He often described mathematics not as a rigid tool, but as a living, expressive language, one that could reveal the invisible architecture of the universe. This philosophy led him to search constantly for deeper insights, and he often brought together ideas from seemingly unrelated domains in pursuit of a more complete understanding of nature. His rooms at Trinity were sparsely furnished but cluttered with books, papers, and hand-built apparatuses. It was common for Maxwell to spend late nights experimenting with physical contraptions to accompany his abstract theories. He built models, spun color wheels, and conducted small experiments to test his hunches, revealing a hands-on curiosity that complemented his abstract reasoning. Despite the rigors of the tripos, he continued to develop independent research, often sketching out new concepts that would later become foundational to his scientific legacy. One of Maxwell's most striking qualities during this period was his originality. He didn't approach problems the way others did. In optics, for instance, he began to study how human vision processes light into color. Using rotating discs with colored segments, he demonstrated that the eye could perceive a mixture of light as a single hue. His work suggested that the perception of color was not a property of light alone, but a consequence of the observer's physiology. This early insight hinted at an interdisciplinary mode of thinking that would define his later contributions. His mathematical gifts continued to garner praise. Though he graduated as second wrangler rather than senior wrangler in 1854, a title many thought he deserved, his subsequent receipt of the Smith's Prize, which emphasized original thinking over rote problem solving, affirmed his intellectual superiority. These distinctions secured his reputation within Cambridge and beyond, and his professors and peers alike recognized in Maxwell a rare combination of imagination, discipline, and vision. After completing his undergraduate studies, Maxwell was elected a Fellow of Trinity College. This fellowship provided both financial support and intellectual freedom, enabling him to pursue original research without the constraints of external employment. During this time, he immersed himself in problems involving elasticity, optics, and the geometry of curved surfaces, subjects that may have appeared disparate, but for Maxwell, they all hinted at deeper symmetries in physical law. The Cambridge environment, though intellectually stimulating, also demanded a certain conformity that never quite suited Maxwell. He was polite, but privately skeptical of rigid academic structures and social posturing. He disliked superficiality and often withdrew from the more performative aspects of college life. Instead, he found companionship in a small circle of students and mentors who shared his passion for deep inquiry. His correspondence from these years is filled with detailed analyses, philosophical reflections, and even poems reflecting the breadth of his mind and the depth of his inner world. It was also at Cambridge that Maxwell began to appreciate the role of historical context in scientific advancement. He studied the works of Newton, Laplace, and especially Faraday, whose intuitive grasp of electricity and magnetism fascinated him. Maxwell recognized that while Faraday lacked formal mathematics, his conceptual breakthroughs in field theory offered something profound, a new way of thinking about the interconnectedness of forces in space. Maxwell began to imagine how this field-centric view might be captured mathematically, planting the seeds for the theory that would later bear his name. Outside the lecture halls, Maxwell found moments of solace and inspiration in nature. He was a frequent walker and an occasional sketcher, often reflecting on natural patterns, from the swirl of water to the symmetry of flower petals. These observations were not idle distractions. They were part of a worldview in which art, nature, and science were different languages speaking about the same truths. He once remarked that nature's laws were written in the language of mathematics, and he was determined to become fluent enough to read them. As the Cambridge chapter of his life drew to a close, Maxwell stood at the threshold of something greater. The youthful prodigy had matured into a disciplined and visionary thinker, though his name had yet to become widely known outside academic circles. Those who worked with him sensed that his best work still lay ahead. In the early 1850s, Saturn's rings represented one of astronomy's most enduring mysteries. Through even the most powerful telescopes of the age, the rings appeared as delicate, luminous bands encircling the planet, and their exact nature provoked intense scientific debate. Were they solid structures, fluid sheets of matter, or perhaps composed of countless individual particles? The question was far from trivial. It touched on broader issues of orbital dynamics, gravitational stability, and celestial mechanics. And it was James Clerk Maxwell, still a young man in his 20s, who would finally bring clarity to this cosmic puzzle. The stage for this breakthrough was set in 1855, when the University of Cambridge announced the Adams Prize competition. The theme that year was drawn from celestial mechanics to determine the physical nature and stability of Saturn's rings. Many saw it as a daunting challenge, best suited for seasoned astronomers with years of observational experience. But Maxwell saw it differently. He approached the problem not with a telescope, but with mathematical insight. His entry, submitted in 1856, would become one of the most important theoretical contributions to astronomy in the 19th century. Titled On the Stability of the Motion of Saturn's Rings, the paper was remarkable in both its depth and originality. Maxwell systematically examined all prevailing theories about the rings. Could they be solid? He demonstrated that such a structure would be inherently unstable. Gravitational perturbations would inevitably tear it apart. A fluid ring, too, would fail, succumbing to waves and instabilities from Saturn's gravitational pull. It was only when Maxwell considered the possibility of countless small particles, each orbiting independently, that the mathematics began to align with physical reality. Using rigorous dynamical calculations, he proved that the only stable configuration for Saturn's rings was that of a swarm of particles, not a continuous mass, but a finely dispersed collection of tiny bodies. Each particle, obeying Newtonian gravity, contributed to the ring's overall structure without risking collapse. Maxwell's conclusion was revolutionary. The majestic rings of Saturn, which had long mystified scientists and poets alike, were not solid bands or fluid sheets, but an intricate dance of debris orchestrated by the laws of motion. What made this work extraordinary was not just the solution itself, but the approach Maxwell took. His mathematical modeling, deeply grounded in Newtonian mechanics, ventured far beyond the observational capabilities of his time. The precision of his reasoning allowed him to make definitive statements about a structure millions of kilometers away, without needing to physically see its components. In this, Maxwell demonstrated the full power of theoretical science to extract truth from abstraction and reveal the hidden order of the universe. The Adams Prize Committee, impressed by the scope and elegance of his work, awarded Maxwell the prize in 1859. But the impact of the paper went far beyond accolades. It marked the first time that stability analysis had been applied to a celestial structure in such a comprehensive way, paving the path for modern dynamical astronomy. The principles Maxwell developed would later influence studies of planetary rings, asteroid belts, and even the formation of galaxies, though the validation of his conclusions would not come for more than a century, until the Voyager missions in the 1980s confirmed that Saturn's rings are indeed composed of countless icy particles. Maxwell's prediction stood the test of time. His method was so sound, so deeply rooted in the physics of motion, that it endured across generations of scientific progress. His mind had reached far beyond the observational limits of his era, anticipating discoveries that would not be visually confirmed until long after his death. This achievement also revealed something essential about Maxwell's intellectual character. He did not shy away from complexity. Where others saw confusion, he saw patterns waiting to be uncovered. He possessed the rare ability to hold a problem in his mind in all its dimensions, to rotate it, dismantle it, and reassemble it into a coherent whole. The Saturn rings paper was more than a solution to a celestial riddle. It was a declaration of his scientific identity. In academic circles, the paper elevated Maxwell's status as a theorist of the highest order. Yet, outside of the scientific community, it remained largely uncelebrated. Maxwell himself, characteristically humble, did not boast of his achievement. He moved on to new problems, always searching for the next hidden harmony in nature. Still, this early triumph cast a long shadow, foreshadowing the even more transformative insights he would offer in the decades ahead. When James Clerk Maxwell accepted his first full professorship at Marischal College in Aberdeen in 1856, he stepped into a role that would test not only his intellectual discipline, but also his ability to communicate complex ideas to a new generation of students. Aberdeen, located in the windswept northeast of Scotland, lacked the cosmopolitan energy of Cambridge or London. Nevertheless, Maxwell saw it not as a detour, but as an opportunity, a place to refine his voice as both a teacher and a theoretician. Marischal College, though modest in reputation compared to other British institutions, provided Maxwell with autonomy and space for research. The curriculum was focused on natural philosophy, which combined elements of classical mechanics, optics, and basic electromagnetism. Maxwell, with his insatiable curiosity, expanded the course content, integrating fresh mathematical approaches and theoretical models. He encouraged students not only to memorize principles, but to question and visualize them. an approach that was rare in British science education at the time. Despite the college's limited resources, Maxwell transformed his lectures into intellectual laboratories. He would often bring physical apparatuses to the classroom, building them himself from wood, string, and lenses. These devices, while simple in design, illustrated complex physical principles with clarity. His students were captivated by the way he made invisible phenomena visible, transforming abstract equations into demonstrable truth. Through this, Maxwell began to build a quiet reputation as both a brilliant thinker and a compelling educator. During this time, Maxwell's personal life also saw significant development. In 1858, he married Catherine Mary Dewar, the daughter of the principal of Marischal College. Their relationship was one of deep companionship and mutual respect. Catherine took an active interest in Maxwell's work, often assisting him in the laboratory and maintaining his correspondence while he became absorbed in his research. Their marriage, though childless, was marked by a quiet harmony that offered Maxwell emotional stability throughout his most productive years. While Aberdeen gave Maxwell the foundation he needed as an academic, it was in London, at King's College, that his intellectual ambitions found full expression. Appointed to the chair of natural philosophy in 1860, he entered the heart of the British scientific world. King's College was a vibrant center of research, and its proximity to the Royal Institution and the Royal Society allowed Maxwell to engage more directly with the leading scientists of the age, including Michael Faraday, whose work had long fascinated him. In London, Maxwell had access to well-equipped laboratories and a larger pool of students. He continued to teach, though now his courses were attended not only by undergraduates, but also by young researchers eager to study under one of the country's most original minds. More importantly, this new environment gave Maxwell the technical support and academic latitude to begin a deep investigation into the nature of electricity and magnetism, subjects that Faraday had explored intuitively but had not expressed mathematically. The King's College laboratories became his workshop for unraveling the invisible. Maxwell devised intricate experimental setups to measure electrical conductivity, magnetic field strength, and the mechanical properties of dielectric materials. He didn't rely solely on speculation. He tested, revised, and retested, ensuring that every theoretical development was tethered to physical reality. It was here that the building blocks of his electromagnetic theory began to assemble, one equation and one experiment at a time. Maxwell also turned his attention to a lingering question in physics: the behavior of electromagnetic fields in empty space. He began to suspect that electric and magnetic phenomena were not simply forces between objects, but the manifestation of changes in a medium, a field that permeated all of space. This radical shift in thinking would eventually lead him to propose that light itself was an electromagnetic wave. But at this stage, these ideas were still forming, still gathering coherence within the crucible of theory and experimentation. London exposed Maxwell to a wider public as well. He gave public lectures at the Royal Institution, engaged in debates, and began to publish more frequently. His reputation, once confined to academic circles, began to grow among intellectuals and industrialists alike. His work on color perception, conducted years earlier, found new life in demonstrations of color photography and spectroscopy. While he remained reserved in public, he was respected, even revered, for the clarity and precision of his thought. By the time Maxwell left King's College in 1865, citing health concerns and a desire for a quieter life, he had laid the essential groundwork for his theory of electromagnetism. The years in Aberdeen and London were not marked by a single revolutionary act, but by a steady accumulation of insights, experiments, and reflections. They were the years in which he bridged Faraday's intuitive genius with mathematical formalism. By the mid-1860s, James Clerk Maxwell was quietly orchestrating a transformation in the physical sciences from his countryside estate in Glenlair, Scotland. Removed from the bustle of London's academic institutions, he immersed himself in the kind of deep, undisturbed thought that had always been most natural to him. It was here, surrounded by rolling fields and distant hills, that Maxwell began to give shape to a vision that had haunted him since his early readings of Faraday. The idea that electric and magnetic phenomena were not separate forces, but interwoven expressions of a deeper unity. The theoretical journey began not with a single breakthrough, but with a series of linked questions. What, Maxwell asked, is the nature of a changing electric field? Could it, like a changing magnetic field, generate its own physical effect? And if electric and magnetic fields could produce one another, could they also propagate together through space? Maxwell approached these problems not through philosophical musing, but by constructing a comprehensive set of mathematical laws, equations that could describe every known electromagnetic phenomenon and predict new ones yet unseen. His work culminated in the publication of a dynamical theory of the electromagnetic field in 1865. In this paper, Maxwell introduced a set of equations that would later be distilled into the famous four Maxwell's equations. These expressions encapsulated the relationships between electric fields, magnetic fields, electric charges, and currents. But beyond the math lay a startling prediction. Electromagnetic waves could exist, and they would travel through space at a specific speed, one that, when calculated from known constants, matched the speed of light with uncanny accuracy. This revelation was nothing short of revolutionary. Light, long considered a separate domain of inquiry, was now identified as an electromagnetic phenomenon. It was neither a mechanical vibration of the ether nor a mystical emanation. It was a wave traveling through a field composed of interlocking electric and magnetic components. Maxwell had unified optics and electromagnetism into a single framework, setting the stage for modern physics. The theoretical implications were profound. If light was an electromagnetic wave, then so too might exist other, as yet undiscovered waves of different frequencies. Maxwell himself speculated on this possibility, but lacked the experimental tools to detect them. Nonetheless, his equations hinted at an entire unseen spectrum, from radio waves to gamma rays. In weaving together electricity, magnetism, and light, he had extended the human understanding of nature's fabric far beyond what could be sensed or seen. What made Maxwell's work so distinctive was not merely the mathematical precision, but the conceptual architecture. He built his theory upon the idea of the field, a mediumless entity that carried force and energy through space. While others still clung to the idea of an invisible ether that transmitted light, Maxwell's field had no need for such scaffolding. It was a radical and abstract notion, difficult for many contemporaries to grasp, but it would later become foundational to all of modern physics, from relativity to quantum mechanics. During this period, Maxwell also refined his concept of displacement current, a term he introduced to resolve an inconsistency in Ampere's law. In doing so, he proposed that a changing electric field could generate a magnetic field even in the absence of conduction current. This subtle addition was essential. It closed the system of equations and allowed them to predict the self-sustaining nature of electromagnetic waves. Without this insight, the theory would have remained incomplete, and the notion of wave propagation through empty space would have been mathematically incoherent. Maxwell's notebooks from this time reveal the meticulous nature of his thought process. He worked through problems in exhaustive detail, often re-deriving results in different ways to ensure their robustness. He annotated his calculations with philosophical musings and analogies drawn from mechanics, elasticity, and fluid dynamics. For Maxwell, mathematics was more than a tool. It was a language capable of capturing the subtlest nuances of physical reality. Despite the elegance of his theory, Maxwell's contemporaries did not immediately grasp its significance. The language of fields and vector calculus was unfamiliar to most physicists of the time, and the abstract nature of the equations made them seem detached from experimental reality. Yet Maxwell was unperturbed by this initial resistance. He had long believed that truth was not a matter of consensus, but of consistency with nature, and he trusted that the future would reveal the depth of what he had uncovered. By the end of the 1860s, Maxwell had created a theoretical edifice that would stand as one of the towering achievements in the history of science. His electromagnetic theory, rooted in precise reasoning and visionary abstraction, redefined not only how physicists viewed light and magnetism, but also how they approached the very concept of force and interaction. Long before quantum theory and relativity reshaped modern physics, James Clerk Maxwell was already probing the invisible dimensions of nature. Though best known for his groundbreaking electromagnetic theory, Maxwell also made profound contributions to the study of thermodynamics, specifically to the kinetic theory of gases. In doing so, he transformed the understanding of matter itself, introducing a statistical approach to physics that would come to define much of scientific inquiry in the 20th century. The fundamental question that drove Maxwell in this domain was simple yet profound. What happens at the microscopic level when a gas is heated, compressed, or expanded? For centuries, gases have been described by empirical laws. Boyle's law, Charles's law, but these offered no insight into the molecular causes behind pressure or temperature. Maxwell aimed to bridge the observable properties of gases with the invisible behavior of their constituent particles. To him, understanding the collective behavior of molecules was key to unlocking the essence of thermodynamic processes. His work in this field began in earnest in the late 1850s and early 1860s, when he built upon the earlier insights of Rudolf Clausius, who had proposed that heat was the result of motion among particles. Maxwell, however, went further. He developed a statistical framework for describing the velocities of gas molecules, not as a fixed value, but as a distribution. This was a major conceptual leap. Rather than seeking deterministic outcomes for each particle, he embraced probability as a tool for understanding nature. In 1860, Maxwell published a paper titled Illustrations of the Dynamical Theory of Gases, in which he introduced what would become known as the Maxwell-Boltzmann distribution. This equation described how molecular speeds in a gas are distributed across a range of values at a given temperature. Most molecules move at moderate speeds, while fewer travel very fast or very slow. The elegance of this distribution lay in its predictive power. It could explain pressure, temperature, and diffusion for first principles. Maxwell's model allowed him to derive expressions for several physical properties, such as viscosity and thermal conductivity, without needing to know the precise details of molecular interactions. For instance, he showed that the viscosity of a gas was independent of its density, a counterintuitive result that was later confirmed experimentally. Such predictions, grounded in abstract mathematics, demonstrated the practical power of the kinetic theory and established Maxwell as one of its chief architects. In parallel with his theoretical work, Maxwell also devised clever thought experiments that illuminated the philosophical dimensions of thermodynamics. One of the most famous of these was Maxwell's demon, a hypothetical creature capable of sorting fast and slow-moving gas molecules without expending energy. The idea, proposed in a letter to a colleague in 1867, challenged the prevailing interpretation of the second law of thermodynamics by introducing the possibility of reversing entropy through information. Though playful in tone, the concept sparked serious debates and would later play a key role in discussions of computation and entropy. Beyond equations and models, Maxwell was fascinated by the implications of disorder and randomness. He recognized that certainty in the realm of molecules was a statistical illusion, a pattern that emerged only when countless particles were considered together. This realization marked a deep philosophical shift in physics. Determinism gave way to probability, and the world became understood not just through forces, but through distributions and likelihoods. In his kinetic theory, Maxwell also collaborated indirectly with Ludwig Boltzmann, the Austrian physicist who further refined the statistical interpretation of thermodynamics. Though their communication was limited, their mutual respect was clear, and Boltzmann would later acknowledge Maxwell as a foundational figure in his work. Together, their ideas formed the bedrock of statistical mechanics, an entire field that would later blossom into quantum statistics and modern thermodynamics. Maxwell's ability to blend mathematics with intuition was particularly evident in his kinetic work. He visualized molecules in motion, colliding like billiard balls in chaotic but predictable patterns. This mechanical imagery, supported by rigorous analysis, allowed him to bridge the macroscopic and microscopic worlds, a feat that few others at the time could manage. Where others saw heat as an abstract quantity, Maxwell saw a teeming universe of particles in perpetual, restless motion. By the time his kinetic theory became widely accepted, Maxwell had already shifted his focus to other pursuits. Yet his contributions to thermodynamics would endure not only in textbooks and laboratories, but in the philosophical underpinnings of physics itself. He had shown that certainty could emerge from chaos, that randomness could yield rules, and that deep physical truths could be teased from the dance of molecules. In 1871, James Clerk Maxwell returned to Cambridge, not as a student nor merely as a theoretician, but as a builder of legacies. The university, recognizing the rising tide of experimental science on the continent and the growing demands of British industry, had committed to establishing a physical laboratory dedicated to research and education. The project had been initiated with a generous donation from William Cavendish, the 7th Duke of Devonshire and former Chancellor of the university. It was to be called the Cavendish Laboratory, and Maxwell was invited to be its first professor and director. For Maxwell, the invitation was both an honor and a challenge. Cambridge had long been a bastion of mathematical physics, but it lacked the kind of experimental facilities that were already flourishing in Germany. Maxwell recognized that if British science was to remain competitive, it needed a dedicated space where theory and practice could meet, where instruments could be crafted, and where young scientists could be trained to observe nature with precision and rigor. Upon accepting the post, Maxwell threw himself into the practicalities of building the laboratory. He oversaw architectural plans, selected apparatuses, and defined the academic vision that would guide its operation. The building, located on Free School Lane, was not grand by modern standards, but it was carefully designed for function. Rooms for delicate experiments, lecture halls for instruction, and workshops for fabricating instruments. Every detail, from gas lighting to insulation, was considered with an experimentalist's eye. More than just a building, Maxwell envisioned the Cavendish Laboratory as a living environment for science. He established a curriculum that emphasized hands-on experimentation, a sharp departure from the purely theoretical teaching style still dominant in much of British higher education. Students were taught not only how to solve equations, but how to calibrate thermometers, measure electrical currents, and use optical devices with meticulous care. Maxwell believed that scientific literacy must include a deep familiarity with the tools of discovery. The role of demonstrator, a position created specifically for the laboratory, was also one of Maxwell's innovations. It allowed for a junior scientist to work alongside students and faculty, offering practical instruction and maintaining equipment. This role became a stepping stone for future greats, including J.J. Thomson and Ernest Rutherford, who would go on to lead the Cavendish Laboratory to world prominence in atomic and nuclear physics. Maxwell thus laid the foundation for a culture of mentorship and collaborative research. Maxwell's own work during this period was quieter but no less significant. Although his days of major theoretical breakthroughs had passed, he continued to refine his previous theories, and he frequently consulted on student projects and experiments. He also began a detailed project to edit and publish the papers of Henry Cavendish, the 18th century scientist after whom the lab was named. Maxwell was fascinated by Cavendish's meticulous and largely unpublished work on electricity, and he recognized its historical and scientific value. The editing of Cavendish's papers was no clerical task. It was a labor of reverence and scholarship. Maxwell painstakingly transcribed, interpreted, and contextualized Cavendish's experiments, some of which had anticipated later discoveries, but had remained hidden in manuscripts. In doing so, Maxwell both honored the past and equipped future generations with a deeper understanding of the foundations upon which modern science was built. The completed volume, published posthumously in 1879, remains a landmark in the history of science. Within the Cavendish Laboratory, Maxwell fostered a spirit of open inquiry and humility. He rejected rigid hierarchies and encouraged students to question assumptions. The culture he nurtured emphasized observation before theory, doubt before dogma. Under his leadership, the lab became not only a site of experimentation, but a sanctuary for curiosity, a place where mistakes were part of the learning process and where every result, however small, contributed to the growing mosaic of scientific knowledge. Despite his declining health, Maxwell remained active in the lab's early years. He lectured, advised, and wrote with undiminished intellectual vigor. Students and colleagues noted his gentle demeanor, his dry wit, and his boundless patience. He inspired loyalty not through authority, but through generosity of spirit and clarity of thought. Even those who found his theories daunting were drawn to his presence, an odd mix of pastoral quiet and scientific intensity. By establishing the Cavendish Laboratory, Maxwell altered the course of British science. What he built was more than a physical institution. It was a methodological revolution. The integration of theoretical understanding with experimental precision became the hallmark of British physics for generations. Under Maxwell's guidance, the seeds were sown for discoveries that would reach far beyond his lifetime, ultimately transforming the laboratory into a cradle of the atomic age. By the early 1870s, James Clerk Maxwell had firmly established himself as one of the leading scientific minds of his generation. His contributions to the fields of electromagnetism, thermodynamics, and the kinetic theory of gases were revolutionary. Yet, despite his intellectual triumphs, Maxwell's health had always been fragile, and his final years were marked by a growing awareness of his own mortality. Maxwell's physical health had been precarious for much of his life. As a child, he had suffered from ill health, including bouts of fever and respiratory issues. As he grew older, his constitution never fully recovered, and he frequently found himself battling fatigue and bouts of depression. By the time he assumed his professorship at the Cavendish Laboratory in 1871, Maxwell was already beginning to experience the first signs of the illness that would later claim his life. In the mid-1870s, Maxwell's health began to deteriorate more significantly. He suffered from persistent stomach ailments, which affected his ability to eat and left him constantly fatigued. In 1879, he was diagnosed with an undisclosed illness that was likely cancer, though at the time, the medical understanding of such conditions was limited. Maxwell's once robust energy was now depleted, and he withdrew somewhat from his usual activities. Despite this, he continued to work and write with the same dedication and intellectual vigor that had characterized his earlier years. His papers from this period reveal a mind still sharp and inquisitive, though often interrupted by physical malaise. During these last years, Maxwell also reflected deeply on the implications of his scientific work. He had long been interested in the philosophical underpinnings of his theories, particularly in the way they related to the broader nature of the universe. In his final letters and correspondences, Maxwell expressed a sense of awe at the complexity and beauty of the laws of nature. He believed that science, in its purest form, was a way of uncovering the mind of God. For him, the mathematical elegance of the universe was not merely a product of chance, but a reflection of a divine order. In 1879, Maxwell visited the United States, where he attended the centenary celebrations of the founding of the United States. The journey was physically taxing, and it became clear that Maxwell was no longer the vibrant figure he once had been. While there, he met with prominent American scientists and delivered a series of lectures on the nature of electromagnetism, but his energy was clearly waning. Despite these challenges, he was deeply respected and admired by the scientific community, and his work was a central topic of conversation at the gatherings he attended. Upon his return to Cambridge, Maxwell's health continued to decline. He was forced to relinquish much of his teaching and administrative duties at the Cavendish Laboratory, although he still remained engaged with the laboratory's work. His colleagues, including J.J. Thomson and Lord Rayleigh, admired his intellect, but could also see the toll that his illness had taken on him. The laboratory, which had been Maxwell's brainchild, continued to flourish, but the man himself was now a shadow of his former self. In the spring of 1879, Maxwell took to his home in Glenlair, seeking the quiet of the Scottish countryside to rest and recover. However, it was clear that his time was running out. On November 5, 1879, at the age of 48, Maxwell died at his home, surrounded by his family. The loss of such a brilliant mind sent ripples throughout the scientific community. Tributes poured in from all over the world, with scientists and scholars acknowledging not only his contributions to physics, but also his character as a teacher, mentor, and friend. Maxwell's death left a profound void in the world of science, but his legacy was already firmly established. His work on electromagnetism had set the stage for the 20th century's most transformative discoveries, from the advent of radio waves to the development of quantum mechanics. The Cavendish Laboratory, which he had helped establish, continued to thrive and became one of the foremost centers of scientific research, producing a long line of Nobel laureates and pioneering physicists. In the years following his death, Maxwell's theories continued to shape the course of physics. Albert Einstein, in particular, was deeply influenced by Maxwell's unification of the electric and magnetic fields, citing it as an important precursor to his own work on the theory of relativity. The idea of fields as fundamental to understanding the universe was something Maxwell had pioneered, and his insights would reverberate through the work of countless scientists in the years to come. Maxwell's personal legacy extended beyond his scientific contributions. He was remembered as a man of humility and integrity, deeply dedicated to the pursuit of knowledge, but also profoundly aware of the limits of human understanding. His colleagues often spoke of his kindness and generosity, and he was known for his ability to engage with young scientists and nurture their development. Even in his final years, Maxwell continued to mentor and inspire those around him, leaving an indelible mark on the next generation of physicists. Though Maxwell's life was brief, his impact on science was immeasurable. His work was not merely a series of discoveries. It was a new way of thinking about the universe, one that integrated abstract mathematical theory with physical experimentation. James Clerk Maxwell's passing in 1879 marked the end of a brilliant life, but the ideas he had seeded in the scientific world blossomed for generations to come. In the years following his death, Maxwell's theories did not simply persist. They became the bedrock of modern physics, shaping the development of countless scientific fields and influencing some of the most profound discoveries of the 20th century. His work laid the foundation for the intellectual revolutions that would redefine how humanity understood the universe. Maxwell's most enduring legacy lies in his unification of the fundamental forces of nature. Prior to Maxwell, electricity and magnetism were seen as distinct phenomena. But his formulation of the Maxwell equations revolutionized the way these forces were understood. His insight, that light itself is an electromagnetic wave, was a radical departure from previous thinking and paved the way for the field of electromagnetic theory, which later became central to understanding everything from radio waves to the behavior of light itself. Maxwell's equations set the stage for later discoveries, including the work of Albert Einstein, who, in his theory of relativity, extended Maxwell's ideas about the nature of light and space. Maxwell's influence on quantum mechanics and statistical physics is equally profound. His statistical approach to the kinetic theory of gases, encapsulated in the Maxwell-Boltzmann distribution, introduced the concept of probability as a fundamental tool in understanding nature at the microscopic level. This was a crucial precursor to the probabilistic nature of quantum theory. Physicists like Max Planck and Niels Bohr built upon Maxwell's foundations, furthering the understanding of atomic and subatomic behavior. His ideas about randomness and order in the molecular world foreshadowed the statistical methods that would later define the study of quantum systems. Furthermore, Maxwell's visionary use of mathematical fields to describe physical phenomena resonated deeply with the theory of relativity that Einstein would propose in the early 20th century. Einstein's equation for the speed of light, which unified the concepts of space and time, mirrored Maxwell's own unification of electric and magnetic fields. Einstein often acknowledged his debt to Maxwell's work, citing it as one of the key influences on his own theories of relativity and space-time. Maxwell's ability to use abstract mathematics to describe the laws of nature without needing a material ether laid the groundwork for a radically new way of thinking about space and time itself. The conceptual leap that Maxwell made in his work on electromagnetic fields also served as a foundation for general relativity. Maxwell's view that light is an electromagnetic wave moving through a field of electric and magnetic forces would later influence Einstein's conception of curved space-time and the propagation of gravitational waves. Maxwell had set the stage for the deep interconnections between fields that would become the hallmark of 20th century theoretical physics. Maxwell's theories also had a profound effect on technology. His work was instrumental in the development of modern communications, from radio waves to television. The equations he formulated described the transmission of electromagnetic waves through space, which would eventually make wireless communication possible. His unification of light with electricity and magnetism provided the theoretical framework for Marconi's invention of the radio and the subsequent technological developments in telecommunication. In addition to his direct influence on science, Maxwell's emphasis on rigorous mathematics and experimentation also shaped the academic environment of the late 19th and early 20th centuries. His establishment of the Cavendish Laboratory provided a model for how science could be conducted in a collaborative, experimental setting, bridging the gap between theory and practice. The laboratory would go on to become a crucible of innovation, producing some of the most significant figures in physics, including J.J. Thomson, Ernest Rutherford, and Lord Rayleigh. These scientists, who were inspired by Maxwell's approach, made their own groundbreaking discoveries, including the identification of the electron and the development of atomic theory. Maxwell's pedagogical influence also extended far beyond his own time. He instilled in his students and colleagues a sense of wonder and discipline in the pursuit of knowledge. His clear explanations and humble demeanor set a standard for scientific mentoring, making him a beloved teacher. His legacy as an educator was carried on by the many scientists who had learned from him, and who, in turn, passed on his methods and enthusiasm for discovery to future generations. Even in fields seemingly unrelated to physics, Maxwell's work echoed his approach to the nature of physical laws, viewing them as universal, elegant, and connected to the very fabric of the cosmos, helped define the intellectual climate of the 19th and 20th centuries. Philosophers, mathematicians, and even poets were inspired by the beauty and simplicity of his equations. His view of science as an orderly exploration of the universe, governed by precise mathematical laws, resonated deeply with the broader intellectual currents of the time. Maxwell's influence on modern scientific thought cannot be overstated. He transformed the way scientists understood the forces of nature and provided the theoretical tools that would lead to the most important discoveries of the 20th century. His work directly influenced Einstein, Heisenberg, and Schrödinger, among others, and his legacy remains a cornerstone of modern physics. His equations continue to be the bedrock upon which the fields of electromagnetism, quantum mechanics, and relativity are built. Beyond the scientific community, Maxwell's life and work remain an enduring testament to the power of intellectual curiosity, perseverance, and the belief that the mysteries of the universe can be understood through reason and mathematics. His dedication to expanding the horizons of human knowledge continues to inspire scientists, engineers, and students worldwide. As both a thinker and a mentor, James Clerk Maxwell's legacy remains as vital today as it was in the 19th century. A reminder that true scientific progress is born from a blend of imagination, rigor, and a profound respect for the laws that govern the universe.